Welcome back, everyone, to another explainer. I am absolutely pumped to guide you through today's topic. We're diving into computer networking basics for hackers. But look, we aren't just going to sit here and talk about routers and dusty cables. No, we're going to treat the network as a dynamic, living digital landscape. It's a terrain that is literally waiting to be mapped, analyzed, and, well, navigated. For an ethical hacker, understanding exactly how data packets are addressed and directed is absolutely critical. It's the only way you can execute precise network mapping and ultimately payload delivery. So let's get into it. Here is our game plan for today. 1. The network transport fabric. 2. MAC addresses and spoofing. 3. The IP addressing grid. 4. Target ports and sockets. And finally, 5. The hacker's terminal toolkit. Starting right off with section 1. The network transport fabric. Okay, so we're going to work bottom up today. We'll start at the physical hardware level and move all the way up to the applications. This is exactly how an ethical hacker builds their mental map during a real-world reconnaissance operation. This network transport fabric is basically the foundational superhighway for all cybersecurity testing. But to really grasp network hacking, you have to understand this one crucial idea from our EC Council source. They point out that local networks operate as a system built on trust, not proof. Think about that for a second. Because local networks lack built-in cryptographic verification for hardware, the network just kind of blindly assumes your device is who it says it is. It takes your word for it. And that inherent trust, that is the exact loophole that ethical hackers and malicious actors both exploit. Which brings us to section 2, MAC addresses and spoofing. Let's talk about layer 2 of the OSI model, which is the physical hardware level. Think of it as the digital bouncer doing an ID check before you can enter the local club. A media access control, or MAC address, is exactly that ID. It's a highly unique 48-bit physical hardware identifier that is literally burned into a network interface card, or NIC, right at the factory. You'll see it written out in hexadecimal digits. Now, the first 24 bits, that's the organizationally unique identifier, basically the vendor code. The rest is a unique serial number. This address routes local traffic within a broadcast domain. It doesn't travel across the global internet. Its main job is just helping the local network switches figure out which physical port to send data to. But remember what we just said about the network lacking cryptographic proof? Yep, that brings us to MAC spoofing. It is surprisingly easy for an attacker to put on a digital disguise. First, they do a little reconnaissance. They passively sniff the network using tools like TCP dump to find the MAC address of a device the network already trusts, like maybe a printer sitting on a secure VLAN. Next up is impersonation. Using a super simple terminal command like IP-link set on a Linux box, they just change their own NIC's reported MAC address to match that trusted printer. Finally, exploitation. They bypass those hardware-based access controls and stroll right past the digital bouncer. To the network, it just looks like the printer doing its normal thing, which, as you can imagine, creates an absolute forensic nightmare in the system logs for incident responders. And attackers can take this deception even further with something called ARP spoofing. So the Address Resolution Protocol, or ARP, is how devices map an IP address to a physical MAC address. But as Wikipedia's documentation highlights, ARP is a completely stateless protocol. Network hosts will automatically cache any ARP replies they receive, even if they never asked for them in the first place. Zero authentication. So an attacker can easily poison the routing table. They just send out spoofed ARP messages telling the network, hey, my MAC address is actually the network's default gateway. The result? A classic man-in-the-middle attack. All the traffic meant for the internet suddenly gets funneled right through the attacker's machine. Moving right along to section 3, the IP addressing grid. So now that we've totally manipulated the local hardware, let's step up a floor to layer 3, the network layer. This is where we trace the logical global routing coordinates to locate assets across the internet. And what is really wild here is the sheer scale of it all. Internet protocol, or IP addresses, are the logical identifiers that route data globally. For decades, we've relied on IPv4. It uses a 32-bit architecture, looks like that super familiar 192.168.1.1, and tops out at around 4.3 billion addresses. But guess what? We ran out of room. Enter IPv6. It introduces a massive 128-bit hexadecimal structure, offering 340 undecillion addresses. That's a 340 with 36 zeros after it. Because this space is so unfathomably huge, IPv6 permits hierarchical address allocation and actually completely eliminates the need for network address translation, or NAT. Now, speaking of NAT,
Under the old IPv4 system, we had to split addresses into private and public just to save space. Private IPs are reserved subnets, like the one you have at your house. They are totally isolated and hide behind network address translation on your router. They can't route directly onto the global internet at all. Public IPs, on the other hand, are fully routable global identifiers assigned by regional internet registries. For an ethical hacker, understanding these IP configurations is absolutely vital. It lets them trace routing paths, figure out if they're looking at an isolated internal network or a public outward-facing server, and ultimately locate their exact target.
All right, let's hit section 4, target ports and sockets. We are moving up one more level to layer 4, the transport layer. Think of this as scanning the outside of a building to find all the virtual doors, windows, and ventilation shafts. The most crucial takeaway here is this specific number, 65,535. That is the vast number of available ports on any given operating system. Ports are basically logical communication endpoints assigned to distinct software processes running on a machine. They're neatly segmented into well-known ports from 0 to 1023, registered ports up to 49,151, and dynamic or private ports filling out the rest. Now, you definitely don't have to memorize every single one, but an ethical hacker relies heavily on scanning these port ranges to figure out exactly what applications are listening for a connection.
When a hacker maps a network, they're hunting for specific vulnerable entry pathways. This cheat sheet right here is exactly the kind of stuff they look for. If they find port 21 open, that means FTP is running, which might just allow them to sniff some clear text credentials. Port 22, that's SSH, a massive target for brute force attacks or key theft. Ports 80 and 443 are your web servers, which swing the door wide open to web app exploits like SQL injection. And port 3389, that is remote desktop protocol. Finding that open is like striking gold for an attacker looking to establish lateral movement across a Windows network. And that brings us to a really foundational concept, the network socket. A socket is simply the specific combination of a layer 3 IP address and a layer 4 port number. Think about it like this. The IP address is the street address of a giant apartment building, right? And the port number is a specific apartment door inside that building. When you combine the two, you create a fully functioning network socket, a precise, logical communication endpoint that software uses to send and receive data. Finally, section 5, the hacker's terminal toolkit.
Okay, we've talked a lot of theory from layer 2 up to layer 4. Let's actually put this into practice and look at a native Linux diagnostic blueprint in action. This is exactly how an ethical hacker or a network defender natively queries a machine during a security assessment. Step 1, you run ip-link show. This pulls up the hardware parameters so you can inspect the link/ether field to locate that active MAC address we talked about. Step 2, IP address show. Here, you look for the inet descriptor to analyze the assigned IP configurations and subnet metrics. Step 3, SSTULPN. This is a total powerhouse command to inspect active logical network sockets and listeners. And step 4, Nmap. Running this executes service protocol and version fingerprinting on those open entry sockets you found. It essentially tells the hacker exactly what software is hiding behind those virtual doors. Let's actually break down that SSTULPN command for a second, because our SANS Institute source emphasizes how important it is. SS stands for socket statistics. By chaining these specific switches together, we get a highly filtered, super useful view of the system. The T is for TCP, the U is for UDP, the L filters for only listening sockets. These are the open doors actively waiting for a connection. The P is absolutely critical. It shows you exactly which software process is tied to that socket. And the N just displays the numeric ports without trying to resolve their names, which speeds up the output dramatically. Hackers use this to instantly isolate active connections and spot vulnerable processes. Here is another incredibly useful trick straight from the Red Hat IP command cheat sheet. IP route get, followed by whatever IP address you're targeting. This quick terminal command instantly displays the exact route an IP address will take to leave the machine. It really proves the value of understanding the underlying routing table. It shows you exactly which network interface and gateway your data or your payload will travel through to hit its target. Well, look at that. We have moved all the way from the physical MAC address through the IP grid up into the transport ports and directly into the Linux command line. You now have a crystal clear view of how an ethical hacker treats your network as a digital landscape that is ready to be mapped, sniffed, and exploited.
So I want to leave you with this final thought. Now that you know exactly how an attacker maps the topography of your network from the bottom up, how will you redesign your defenses to stop them? Seriously, think about it. It's a whole different ballgame once you see it from their perspective. Thanks so much for joining me on this explainer, and keep learning.